my channel Priyanka's Learn It Well, and today and for the next few episodes I'll be covering the asymptotic notations, its application, the properties of asymptotic notation, master theorem for divide and conquer, and it will be done with the help of certain examples. So stay tuned for this and another 2 episodes coming up for learning the concepts of asymptotic notations in data structures and algorithms. If you like my content, do not forget to like, share and subscribe my channel and hit the bell icon for all the notifications from Priyanka's Learn It Well. So let's start with today's episode.
Asymptotic notations are the very important part of data structure and analysis. Asymptotic notations are meaningful approximations of functions that represents time and space complexity. Having the expressions for the best, average and worst cases for all the 3 cases, we need to identify the upper and the lower bounds. To represent these upper and lower bounds, we need some kind of syntax, and that is the subject of the following discussion, that is the asymptotic notations. The big O notation gives the tight upper bound of the given function. Generally, it is represented as fn is equal to O of gn. O notation is defined as O of gn, that is f of n, that is the function of n, if there exists a positive constant c and n naught such that fn is less than or equal to c of gn for all n greater than or equal to n naught. Let's say f of n is equals to big O of gn if and only if f of n is equal to, or you can say f of n is less than or equal to c of gn, where c is a positive integer, and where n is greater than or equal to n naught. In the diagram, you can see that c of gn is the upper bound of the function f of n. For example, if the value of f of n is given as 3n plus 8, to calculate the upper bound for the same, we will be putting up the formula as f of n is less than or equal to c of gn. We will now put or substitute the value of fn into this formula, that is f of n should be less than or equal to c of g. Right hand side should be greater than the term on the left hand side. What we can do is we can simply put the value of n with 8 as well. So we can replace the value of c dot gn as 3n plus 8n. So putting the value of n with 8, we get for all n greater than or equal to 1 or n naught is equals to 1, 3n plus 8 is less than or equal to 11n, where the value of c is 11. This is not only the way to find out the upper bound. The only thing to ensure is that we need to keep the RHS greater than the left hand side. But here that would be for all n that is greater than or equal to 8, and here we find the value of n naught is equals to 8 and c is equals to here it is 4. There were 2 ways. With one, we have found that 3n plus 8 is less than or equal to 11 of n, and thus we said that f of n is equals to big O of n. Now, we can have different upper bounds as well. I have given an increasing order of rate of growth here. So, you can see that this is the increasing order of rate of growth of functions, and when I move to the right hand side of the function, that will be included in the upper bound, and anything below the function would be the lower bound. So for the n, you can see here that we have different values: n log n, n square, n cube, 2n, 2 to the power n, 4 to the power n, and so on. So here I can say that fn is equals to O of n is valid upper bound, f of n is equals to O of n square is valid upper bound, f of n is equals to big O of 4 to the power n is also an acceptable upper bound. But if I have to write down the notation, the big O notation for the function 3n plus 1, the closest function would be the closest function that I can take is big O of n. Moving to the big omega notation, that is the representation of the tight lower bound on a function. So, omega notation is defined as the big omega of gn when f of n there for f of n there exists a positive constant c and n naught such that c of gn is less than or equal to the function n, that is f of n, for all n greater than or equal to n. When we write the function, so f of n is equals to omega of g of n when f of n is greater than or equal to c of gn, where c is the constant, and for n greater than or equal to n naught. Let's take the same example, that is fn is equals to 3n plus 8, and we would be writing it as 3n plus 8 is greater than or equal to 2 of f, 2 of n. Either you can write a value that is lesser than this number, that is 3n, or you can simply remove this value from here, that is 3n plus 8 is greater than or equal to 2n, or you can even write 3n plus 8 is greater than or equal to n. It is always good if you can remove this value, you'll get easily the value on the RHS. Looking at the increasing order of rate of growth here, so any value that falls below the function that we have found is, that is omega of n, will be appropriate or acceptable for the lower bound of the function. So let's say if I write f of omega of n, that is there, f of n is equals to omega of log n, f of n is equals to omega of 1. These three are acceptable lower bounds because it falls on the lower side of the function, but we'll be taking the closest of the three functions, or the functions that are acceptable. Let us take one more example for big omega. F of n is given as 3n square plus 1. Putting the expression f of n should be greater than or equal to c of gn, and substituting the value of fn as 3n square plus 1 should be greater than or equal to. Now what I have done is I have simply removed the coefficient from here, and I get the value as n square, and hence f of n is equals to big omega of n square. Again, there are several possibilities to this lower bound. F of n is equals to big omega of n log n, because you can see that the n square, anything on the left hand side of n square can be treated as the lower bound. So if I say big omega of n log n or big omega of 1, these are acceptable lower bound for the function 3n square plus 1. The third is the theta notation. The theta notation is defined as when f for fn there exists a positive constant c and n naught such that c1 of gn, fn lies between c1 of gn and c2 of gn, where c1 gn is the lower bound and the c2 dot gn is the upper bound. So here for the function we'll be looking at the lower bound and the upper bound. So we are seeing the average case with the help of theta notation. Let's take the similar example. F of n is equals to 3 of n, 3n plus 8. We have already calculated c1 dot gn in the previous slides. So we got the lower bound as n, and we got the upper bound as 11 of n. So on the left hand side we have c1's value as 1 and gn is equals to n, whereas on the upper bound we are having the value of c2 as 11 and gn as n. Hence, we get the theta notation for the function 3n plus 8 as theta of n. Now, as with the previous example, let's see if we can have other values other than theta of n. So, there are three options that I have given. F of n is equals to theta of n, f of n is equals to theta of 1, and f of n is theta of 4n. So here only f of n is equals to theta of n will be considered. No value above or below the particular function would be treated as the average case analysis. To summarize with what we have done till now, we have studied three asymptotic notations. Big O that represents the upper bound and the worst case, big omega that shows the lower bound and the best case, theta shows the average case. Asymptotic notation we have done for the a priori analysis. There are several helpful guidelines for asymptotic analysis. Let's say we want to analyze a code with loops. The running time of the loops is at most the running time of statements inside the loop multiplied by the number of iterations. So we can see that for this code snippet, there is just one statement inside this loop, and the number of iterations is given by I is less than or equal to n. So we have n number of iterations. So when we calculate the total time for that, so the statement is having a constant time c, and the for loop will execute for n times. So the total time will be calculated as c into n. If we want to represent, then C into n, Cn, and the complexity is given as O of n. Nested loops. Analyzed from inside out, the total running time is the product of sizes of all the loops. So let's say that we would be analyzing the innermost portion of the code. So here I have a statement that has a constant time that is under an inner loop that executes for n times, so n iterations, and this again is under a outer loop that is for n times. So here you can see that this is not the outer loop, this is the inner loop. So if we multiply each of them, so we get the total time as c into n, that is cn square. So the total time is given as O of n square. The next is the consecutive statements. With the current code snippet, you can see that there are different consecutive statements. So we'll be calculating their complexity and adding them with each other. So the first is the x is equals to x plus 1, that is a constant time. Then there is a loop and a statement that would be a constant time c, and it performs for n iteration c into n. And then there is a nested loop, so we'll get c into n into n. So for each of these three blocks, we'll add them up and we'll get the total time as c0 plus c1n plus c2 n square, where c0, c1 and c2 are three different constants for the statements with the code snippet. And discarding the lower order and considering the higher order, we get the total time as O of n square. The next very important part is the logarithmic complexity. An algorithm is O of log n if it takes a constant time to cut the problem size by a fraction, usually by half. And to take an example, we have a code snippet for I is equals to 1, I is less than or equal to n, I is equals to I into 2. So if we observe, the value of I is doubling every time. Initially it was 1, the next time it becomes 2, 4, 8, and then so on. Let us assume that the loop is executing some k times, so at kth step. So taking the logarithm on the both side, we'll get log of 2 to the power k is equals to log of n. K log 2 is equals to log n, and on solving, we get the value of k is equals to log of n, and hence the total time is O of log n. Similarly, we have a case where I is equals to n, I is less than or equal to 1, and I is equals to I by 2. So here again, the complexity would be derived as O of log n. That is all from this episode of Asymptotic Notation Introduction. In the next upcoming episode, we would be taking up some examples and master theorem for divide and conquer problems.